you go ahead and get started.
Okay, so this is part two. Today's talk is called Complex Orientation and the Morava K-theories. So I hope to introduce both of those things. But okay, so before we jump into the new stuff, let's just do a quick review of what we did last time. So last time, I introduced the category of spectra. These were sequences of spaces together with certain structure maps. And we talked about the stable homotopy category SH. So I didn't say much about SH, but I did say that we were going to work with it axiomatically. So it's a closed symmetric monodal triangulated category, and its objects represents homology and cohomology theories. SH is obtained from spectra by formally inverting all of the pi star isomorphisms. So those are called weak equivalences, but they're also the isomorphism for the homology theory represented by the sphere spectrum S0. So once we were done with that, then we turned to Bell field localization. We said, well, why not invert other types of isomorphisms? So if E is another spectrum, we talked about E-local spectra. So the category SHE was obtained from spectra by inverting not the S0 star isomorphism, but the E star isomorphisms. And then I discussed E-local spectra, what that meant. So why is E-local? If whenever E star of Z is 0, so if this is E is cyclic, then maps from Z to Y are completely trivial or zero. Okay, so E is cyclics and E-local spectra are sort of orthogonal. And then we discussed E-localization. So an E-localization was a map from X to an E-local spectrum. And it had you had the following properties. So suppose that you have a map from X to another E-local spectrum Y, then that map factored uniquely up to homotopy, so in the stable homotopy category. And this localization map had the property that it was an E star isomorphism, and this was E-local. Okay. And then we talked about examples of them, but for now, that's all I will remind. Okay. Okay, so today, I hope to cover at least most of the following topics. So I'll let you take a glance at them instead of just reading them out. So I'll dive into it. So I mean, these things, like if you know what they are, you know what they are. Great. If you don't, then you'll know at the end. So there you go. Okay, so before I jump into the new topics, first I need one more definition. So that of ring objects, and I guess in SH. So if I have a spectrum E, I'm going to say that it's a homotopy ring spectrum. And for today, it's just always going to be homotopy rings. If it's a ring object in the stable homotopy category. So what does that mean? In particular, E has a unit. Okay, so that's a map from S0 to E, and it has a multiplication. So that's a map from the smash product of E with itself to E, and they have to satisfy the diagrams of a ring object in the category of SH. So if you think about what associativity is, and you try to sort of write a commutative diagram that sort of represents that happening, then those are the diagrams you're looking for, and you want them to happen for this E. Now we'll say that E is homotopy commutative if this diagram commutes. So here, sigma, remember SH is a symmetric monodal category, so there's like a structure map for the symmetric part of the modal category. So there's always a map. So there's a map sigma from like so. And so if E is a ring spectrum, that it has these multiplication maps here, and we want this diagram to commute. All right, if we have such an E, then pi star is going to be a graded ring, and it's going to be graded commutative if E is commutative. Okay, so you pick up signs when you switch elements. All right, so that's what I'll mean by rings. Okay, and maps between rings are what you think they are. All right, so now I'm ready to do the first definition for today. So this definition is important, so I'm going to take time to make sure that you have a little bit of time to absorb it. So, all right, so we're going to have E here is going to be a homotopy ring spectrum. And we're going to say that a complex orientation for E, it's going to be a class. So if I need to say, like if I need to distinguish E from other things, I'll write X upper E, but for now I'll just write X. And this is a class in the second cohomology of CP infinity for E. Okay, and we don't want any class. We want a class that, okay, so if I have, so remember S2 is CP1, and that sits as the 2 skeleton of CP infinity. So that's a map of spaces. So we get a map on E cohomology. So you get a map from E2 of CP infinity to E2 of S2. And the suspension isomorphism gives that E2S2 is pi naught of E. Okay, and remember E is a ring spectrum, and what do we want? We want that X goes to 1, the unit, okay, in pi naught of E. So if these things are satisfied, we say that X is a complex orientation for E, okay? So E is complex orientable if there exists an orientation, but today I'm going to talk about complex oriented theories. It means you've chosen one, okay? Okay, so let's go through the first example, which should be very familiar. So, okay, so CP infinity classifies complex line bundles, okay? So there's a tautological line bundle. So if you have a line, then you just, the line bundle is like the fiber over a point is the vectors on that line. So that's the tautological line bundle. Now, HZ is just your favorite cohomology theory. And the cohomology of CP infinity, if you remember, is polynomial on a class X. And this class X is in H2 of CP infinity, okay? And you can think of it, it's the first Turing class of gamma 1. That's one way you could say it. But if you make this choice, then this is going to be a complex orientation. So that choice of class in H2, so remember we're looking for a class in E upper 2, so H upper 2 is going to be a complex orientation. So remember if I do, okay, so if I go to HZ2 of CP1, that's, you know, that's HZ2 of Z, which, sorry, not Z, of S2, and that's Z, right? And I mean, if you've done the computations for the cohomology of CP infinity, if you take a generator of this group, you know that it goes to a generator. So in fact, so I'm going to write something, and maybe at first that's going to be confusing. So I'm going to write that the cohomology of CP infinity, it's HZ star. So what do I mean by HZ star? Remember, so HZ star is equal to HZ lower star is pi minus star of HZ. Okay, so that was the notation we introduced last time. Now I say that it's so, and for this it's just, you know, Z in degree 0. And then I'm writing a joint of power series on X. So now you're like, okay, well, polynomial rings and power series ring are not actually the same thing, but now we need to sort of point out that something that happens in algebraic topology, we write rings, but we say rings, and we treat them like rings, and we give them the expressions like these polynomial rings and whatnot, but we always only mean the homogeneous elements in those rings, okay? So if you think about the homogeneous elements, so the polynomials that have like only monomials of the same degree, if you look at the homogeneous elements in that and the homogeneous element in here, then, so homogeneous in here and homogeneous in here, then these things are the same, okay? So to a topologist, these rings are the same. All right, so that's that. So
can I ask
a
question?
Yeah.
Can you explain what you mean by you're really only considering the homogeneous elements? I mean, I understand the statement, but why or to what capacity are you only considering homogeneous elements?
Well, like, so like, I would never write something like A plus B, where A is in HN and B is in HN.
Okay.
Like when I say that what's the cohomology, it's a graded abelian group in the sense that it's a sequence of abelian groups. And then I also have a pairing between the nth and the nth group going into the nth.
You only think about the classes separately and their different gradings.
Yeah, you don't like add things that are in different degrees. Okay. And all our ring, like when I write that this is a ring, I mean, it's like in degree n, it's the homogeneous elements in that thing in degree n.
Got it.
Okay, and that somehow we all do this and we don't say it, but this is a place where suddenly it becomes confusing, maybe the first time.
Got it.
Did that answer your question?
Yeah.
Okay. All right, so now let's look at other examples. So let's look at complex K theory. So beta and pi 2 okay is going to be the Bach class. Okay. So gamma 1 again is the tautological line bundle on CP infinity. So there's a virtual bundle gamma 1 minus 1 in just K0 of CP infinity. And you know, if you read Atiyah or Hatcher's vector bundles on K theory, you'll see that the cohomology, the K theory of CP infinity is, you know, you have Z adjoined the Bach class and then a power series ring on this virtual bundle. Okay. So now I want a class in K2. So I'm going to take this guy here and I'm going to move it to K2, K upper 2. Okay, so there's a, like, you know, there's a plus, and if I put the 2 up and the 2 down, there's a switch by a minus sign here. And this is going to be a complex orientation. So you can just, you know, you can look at the map to K2 of CP1 and you'll find out that picks out a generator. And in fact, again, now there's nothing confusing about writing the power series ring. It's sort of a little bit closer to our intuition. And the K theory of CP infinity is K star. So the K theory is a point. So this is Z adjoin beta plus or minus 1 adjoin power series on this orientation. Okay.
Agnes,
So the final example, was there another question?
Yeah.
Okay.
So I think I understood what you were saying about, like, oh, the power series ring and the polynomial ring are the same because you're just doing them in this graded way. Is there like a reason to prefer writing it as a power series ring?
It's like such great notation, right? We all know what it means.
No, but I mean, why not just have it be the polynomial ring?
Oh,
Like,
here, okay, so here it actually is a power series, right? It's the when there's a chance for it to be a difference. So here you see, I'm about to say this about MU2. When there's a chance to be a difference, it's the power series choice.
I see.
So
okay.
here you do have like infinite tails, okay? Because this guy here is in 0, in degree 0. I can take infinite powers of this thing and stay in the same degree. So like this class here, if I take it to the M, it still has degree 0.
I
so
see.
then
Okay.
I need the formal completion. So yeah, so the right thing to say it's that it's the formal completion. Otherwise, I'd just do the power series because it's maybe an easier ring to think about. Okay. All right. So did that answer the question?
Yeah. Great. Thanks.
All right. So now let's see. Okay. So CP infinity, another name for it is BU1. Okay. Or BS1. So and remember we constructed the complex cobordism spectrum using, you know, the spaces MUN, which were the Tom space of the tautological bundle on BUN. So if I look at, so I take gamma 1, the bundle again, the tautological bundle. I take the Tom space on gamma 1. That's MU1. That was the definition. And there's a 0 section. Okay, so you can, like, it's a vector bundle, right? You can put CP infinity at the zeros everywhere. And what you've done for the Tom space is you've crushed everything at infinity, but the 0 section was left intact. Okay. Now, it turns out that this is a homotopy equivalence. So a lot of the stuff I say today, so Adams, the blue book. So if you don't know what the blue book is, it's stable homotopy theory, stable something. It's on my, there's no link on my webpage to a PDF because I didn't find one, but the name of the book is on the webpage, and it's parts 1 and 2 is a nice place to read about this. Okay. All right. So there you'll see that he discussed why it's a homotopy equivalence, and then you so you get a class which is, you know, the 0 section is a map from CP infinity to MU1. But MU2 here, what do I mean by that? I mean the second space of, the second space. So as in not the 0th, not the 1st, the 2nd, okay? So the 3rd, you know what I mean? The number 2 space of the spectrum MU. Well, MU was built from these MUN, and in particular, if you go back to the construction, there's a map from MU1 to MU2. So if you take CP infinity to MU1 and then you go into the second space of the spectrum, then you get a class. That's exactly what the cohomology was. It was classified by these maps, so you get a class in MU2 of CP infinity. And this turns out this is a complex orientation. And in fact, MU star of CP infinity is going to be MU star of a point. Remember, MU star was Z of X1, X2, dot, 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 where the Xi are in M2I. So this is MU minus star. And again, completed on X. Okay. Okay, so there's a clear pattern. Yeah.
This is Dan.
Yeah.
I've noticed that in all your examples so far, E star of CP infinity is just E star power series in X. Is that going to be true forever? Are we going to see examples where that doesn't hold and so forth?
So I just switched slides to answer your question. So your question is an exercise, is that if E is complex oriented, this is true.
Okay.
This is not true in general, but for complex oriented theories, it's true. And there's a reason why I pointed that out. It was building up to this slide so that you'd have this question in your head. Okay.
Sorry, I jumped in.
No, this is fine. So it worked. So if you have a complex oriented theory with your orientation X is equal to XE, then in general, so if you take the E homology of CP infinity, so Dan's question is about when M is equal to 1, okay, when this little M is equal to 1, but it's true just like you take a product of them, then the cohomology is going to be power series on so E star, that's often called the coefficients. So the coefficients of the theory, power series on M generators. Okay, so in particular, it works for 1. Okay, and then in fact, if you look at the cohomology of BU, then what you'll get E star power series on classes C1, C2, and so on, where Ci is in degree 2I. And that should remind you of the cohomology of like the regular singular cohomology of BU, because these guys, these Ci's, they're Chern classes for the theory. Okay, so complex oriented theories have theories of Chern classes. That's their jazz. Okay. So this.
Sorry to interrupt, and yes, I think someone had raised their hand. Is there another question out there?
Oh, I had a question, but I can see that.
Okay.
Okay. So you can look in atoms. The proof is there, but you can also. This is like if you know what the Atiyah-Hirzebruch spectral sequence is. This is a fun exercise to think about using the Atiyah-Hirzebruch spectral sequence. Okay. And then, okay, so BU1 and CP infinity are one and the same, and there's a map from BU1 to BU, and this map here is going to take C1 to the orientation X, okay? So this X here is like the first Chern class. Okay, that's its role in life. Okay. All right, so now let's see. I'm building up towards defining to you what formal group laws are, but first I need one more thing. So let's look at some structure that's just lying around for us now. All right, so CP infinity times CP infinity, that classifies the tensor product of line bundles. Okay, so if you have a map into CP infinity cross CP infinity, then that classifies the tensor product of two line bundles that you had. But there's the map that so this map here that classifies the universal tensor, which is sorry, that's the wrong symbol. So it's gamma times 1 tensored 1 cross gamma 1. So this bundle over CP infinity cross, so this is over this, is classified by the tensor product. Okay, so this is the map that makes CP infinity into an H space. You can describe it in terms of algebraic geometry. There's tons of ways to think about this. Okay, but whichever way you pick, you get a map. So this is a map of spaces. So you get a wrong way map in cohomology, or just a map going the other way in cohomology. And remember, so if you do the exercise, you'll have this isomorphism and this isomorphism. So you'll know that the sides are both power series ring. And now, okay, so you have your orientation. You can look at its image under this map. Well, that lives in this group, right? So it lives, or this ring, it lives in a power series ring. So it's a power series in two variables, okay? And now, so it's what it is, okay? So you don't know. It could be a lot of different things. But I'm gonna use, so this is important notation, so maybe I'll even use a different color. So I'm gonna use this notation here. So what does this mean? It just means that, okay? X plus sub Fy is just a formal symbol that means the power series F of Xy, okay? But the useful thing for the symbol, like this notation is just gonna make everything sort of feel natural. So that's why we have to sort of accept it and internalize it, okay? So X plus sub Fy is just power series in two variables, X and Y, and it's the image of X under this map. All right, similarly, gamma 1 has a C-linear dual. Vector bundles, you can do duals. There's a map that classifies that C-linear dual. And then we're gonna let I of X be the image of the orientation under that map in ecohomology. Okay. Now, if you go back to what I said before, so X was supposed to be this first Chern class, right? So what is this thing, F of C1 and C2? Well, it's actually, this power series here is actually the rule for what's the first Chern class of the tensor product of two line bundles. So if you remember in the classical, in the classical story, sorry, I meant C1. I'm missing another one. So the first Chern class of the tensor product of line bundles, of two line bundles, is the sum of the Chern classes, okay? So, but in general, for complex-oriented theories, there's always a formula, and it's this power series. That's what it's giving it to you. But now, tensor product has lots of nice property. It's associative, it's commutative. If you tensored with a trivial bundle, then it's like you did nothing. Okay, so 0 is like standing for the trivial line bundle, okay? And if you tensor L with its dual, then you get a trivial bundle, okay? So all these properties of the tensor product says that the first Chern class of the tensor product of line bundle has to satisfy certain symmetries. You know, whatever formula you got for it has to have certain symmetries, and these symmetries are these 4 properties, okay? So if you're confused, so like this one here, if I translate in terms of power series, it means that I have to have this, okay? All right, so now let's put that, okay, so now we've got objects that have properties. Let's put them in a category. So let's look at the category of formal group laws. So now I'm gonna do a swap from homological to cohomological to homological grading. Remember, like X was in E2 of CP infinity, okay? So if I'm thinking of homological grading, that puts X in degree -2, okay? Because the 2 becomes -2. So there's, I mean, later on, it'll just be easier to just be in homological grading. So, all right, so if you have a graded ring, you can look at this power series ring, and you grade it by letting X and Y be in degree -2 because of the reason I just said. Then we're gonna define a category of formal group laws over R, okay? So a formal group law, which sometimes I'll abbreviate like that, is just gonna be a power series in degree -2, okay? So that's just emulating the situation we had before. And we're gonna stick to this notation. Okay, and then it has to satisfy the properties 1 through 4. So for a second, let me go back. So it satisfied these properties here. Okay. All right. So that's a formal group law. Now I've got objects, so I need morphisms. Now for a second, just imagine that F and G are groups, okay? And that we have this nice slick notation of addition. Well, if you had a group homomorphism, this is what you would require, right? You'd require that applying F to a sum is the same as summing the results that you get, okay? Well, that's exactly what we're gonna ask. So we're gonna say that morphism, well, it's gonna be a power series in degree -2 that has no constant term, okay? And that satisfies this identity. So let me translate it in terms of power series for you. That's, so if I apply F to this result, I get G of F of X and F of Y. Okay, so that's how that translates. And if you look at this, the identity is just like the power series, that's just X. And then there's one more construction that I need. It's that of base change. So if I have I have a ring R, a graded ring R, and a graded ring S, and I have a ring homomorphism between them, so of graded rings, then I can apply this phi to the coefficients of the power series and of the morphism. I just apply the coefficients, and that gives a functor between formal group law over R and formal group law over S, and I'm just going to call that base change.
Okay.
All right.
I have a question.
Yeah.
Up here, when you said that you're defining a formal group law, and you say that it's homogeneous of degree -2.
Mm-hmm.
But for instance, isn't the multiplicative law, the multiplicative group law isn't even homogeneous?
So there's two ways you can think. So there's a story that isn't homogeneous. I chose to tell the homogeneous story. And look, this is what I'm going to call the multiplicative group law. So I'm working over graded rings. I could have said this not graded rings. If I wasn't working in a graded context, I wouldn't have put a homogeneous condition. Okay? So whenever you have a unit, like with these periodic theories, like K theory, you have this unit, you can move the story to degree 0.
Okay.
By that unit.
I see. Okay.
Okay, so you can, but there's some theories that don't have that unit, like MU doesn't have a unit like that you can move things around. So if you want to tell the story for MU star, that's where we're going, then you need to work with the graded context. Okay? So you're welcome. If you forget the grading, then there's some things that you can say different. Okay. All right, so fx plus y is x plus y. Well, that's just, we just said C1 tensor L2 is C1 L1 plus C1 L2. And then, in K theory, so if you take C1 of L, then you get something like L minus 1. And this is not, so here I haven't put it in the right degree, so you have to like multiply it with probably beta, or beta minus 1. I'm usually going to put plus or minus 1. I don't know off the top of my head. So if I try to think about it, I'll get confused. So the multiplicative formal group law is supposed to be the rule for Chern classes in K theory. So, and you'll get something that I'm going to write like this. You can write it a lot easier. You can write x plus y plus beta xy. Okay, but I'm going to use this formulation because it's going to be nice later. All right, so that's two examples. Okay, but I mean, now you get the pattern. I'm going to do HQ, K, and then I'm going to do MU. So the next slide is going to be about MU. Okay. So this slide is about, so this is going to be combining a theorem of Lazare and a theorem of Quillen. Okay, and what does it say? So what's the formal group law MU for MU? Well, it's something called the universal formal group law. Okay, so it's the mother of all formal group laws. So you can write fxy of MU in like, so the most generic form you could think of for a power series. Okay, it's just a power series and two variables. And then but now so this is initially defined over this ring where you just adjoin the aij's to Z. Okay. But that won't be a formal group law. There's a bunch of relations that have to happen for properties 1 through 4 to be true, okay? And I is gonna be the ideal that generates these relations. So for example, A00 has to be 0, okay? And A10 has to be 1, and that has to be equal to A01. Okay? So there's a ton of relations on this thing, okay? But whatever they are, this thing is the universal formal group law. Okay, so it's the thing that's going to have the property that I'm going to talk about here. Let me jump to that. So if you have any other formal group law, then there's a homomorphism from this ring here, where you take all of this stuff and you modify I to R star, such that if you apply phi to the coefficients of this gadget here, you get the formal group law F. Okay, so that's what it means to be universal. It means that formal group laws over R R star, just the objects are represented by Homs from mu star to R star. Okay. So now it's a theorem of Lazard that L, so it's a theorem of Lazard, no, not that isomorphism, sorry. It's a theorem of Lazard that L is isomorphic to a power series ring in countably many variables, okay? So, and the xi, remember, are in M2i, so they're in degree 2i. And it's a theorem of Quillen that's also mu star. Well, okay, so maybe people knew mu star before Quillen, I don't know. But Quillen's theorem is that FMU is the universal formal group law. Okay. And in fact, okay, so if you start writing things down, you'll see that the first coefficient, the first x1 you can think of as the coefficient of x times y. But then after that, like the xi, I mean, it's hard to write who the xi is, what role they're playing, right? You went from having like a power series ring on like a double index set of generators to, sorry, a polynomial ring on a double index set of generators to one on a single index set of generators. There's a lot of carnage in this ideal, okay? All right, so now that's like the algebraic part of Quillen's theorem, is that mu, like you look at its formal group law, then like if you want another formal group law, there's a map from mu star to r star that gives you that formal group law by just applying phi to the coefficients of this gadget, But then we're interested in topology, and so this refines. So in fact, if you have a complex-oriented theory with its formal group law Fe, then there's actually a map of homotopy rings that classifies that formal group law in the sense that if you look at, so pi star of F, that's a map from mu star to E star, then you can apply that ring homomorphism to FMU, and then you'll get Fe. Okay. So in the sense like, okay, you have a complex-oriented theory, it has a formal group law, that's classified by a map from mu star to E star, but that map actually came from homotopy. Okay. So that's also in Adam's blue book, and it's in part 2. And so the realization is another application of the Atiyah-Herzebruch spectral sequence. All right, so that's story. So FMU is the universal gadget. So complex-oriented theory are the same as, you know, like theories with, so the complex-oriented theories come with the homotopy ring map from MU that classifies their formal group law. All right, so now I'm gonna move on to the next topic. So my next goal is to talk about heights, but first I need to sort of give a couple definitions that we're gonna need to make the other definitions. So suppose you have any integer and a formal group law f over r, then let's define this series here. So that's just like fx, dot, 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 f, I guess you end with xx or something, okay? So where you see like n x's in there. Well, in the category of formal group law, that'll be a morphism. For any integer, it'll be a morphism from f to f. And we're gonna call, this morphism is called the n series. So for example, this is the formal group law for rational homology. Then if you just look at, you do this process, you'll just get n times x, okay? This is the formal group for K-theory. And now the reason I wrote it this way is that then it's, now you can go home and check that the n series for K-theory looks like this, okay? So it's really easy to derive this formula from this expression, okay? You just compose. Okay, so that's the n series. And now we're gonna, so now this is the part in the lecture where we start fixing a prime, okay? So P here, I'm always gonna mean P a prime number, okay? So now at this point, we're gonna start looking P locally and we're gonna see these patterns, okay? So we're gonna let Vn, that's gonna be an element in pi 2 times P to the n minus 1 of mu. And it's just gonna be defined to be the coefficients of this term here, x P to the n in the P series. Remember, we've picked a prime in the P series for FMU. So Vn depends on P, but we don't write the dependence usually, so I won't write the dependence. Okay, so for each P, there's a family of Vn's. Okay? So for example, V0, so P is V0, right? Because the first term has to be Px, you can check that. And so V1 is the coefficients of x to the P, and so on. And if you mod out by everything that came before, then you'll get that Vn is congruent to x to the P to the nth minus 1 generator in pi star nu. So, all right, so now with this in hand, we can define the height. Okay. So suppose we have a formal group law over R star, and it's classified by some map from mu star to R star, because that's the property, universal property of mu star. Then suppose that so, you know, the Vn's, they live in here. So if that doesn't go the right way, the Vn's live in here. If phi Vn is a unit in this ring R star, then we're going to say that f has height at most n, so less than or equal to n. Now, if on top of that, all of the previous Vi's went to 0, then we'll say that f has a height exactly n. Okay. So there are different sort of ways to say this out there, but this is a good simple way to say it. Okay. All right, so FHQ has height 0 at any prime, because you remember the n series was n times x, so the p series is p times x, that's V0, and that's invertible, like p is a unit in Q because it's not 0. Similarly, K-theory has height less than or equal to 1 at every prime. So because if you take the formula I gave you, you'll get px plus a bunch of binomial coefficients which are divisible by p, and then the last term you'll get the Bach class to the p minus 1 times x to the p. And this is a unit because k star is z beta plus or minus 1. Okay, that's Bach periodicity. Now, if you look at mod pk theory instead, which is just k smashed with a mod p Moore spectrum, the effect on k theory is just to mod out by p, the coefficients. Okay. So if you take the formula that we have here and you mod it out by p, then all you get that's left is this term. So that means that mod pk theory is height exactly 1. Okay. All right, so these are examples. Let's see, I'm not gonna do mu because mu doesn't, I mean, it has a height less than or equal to infinity, right? It just, there's not gonna be any units because they're all like congruent to x p to the n because of this part, okay? All right, so that's the height. And okay, so the next thing, now I'm gonna use this construction and these VNs to construct new theories from old theories. Remember, one of the goals for today is to talk about the Morava K theories, and we're almost there, okay? All right, so if you have a ring homomorphism from mu star to R, then you can consider the functor, which takes base CW complexes to abelian groups, and it so from base CW complex to abelian groups, and it takes X to just this abelian group. Okay, that's actually an R star module. But now this looks like it wants to be a homology theory. The fact that you're plugging in mu star of X is going to give you homotopy invariance, the suspension isomorphism, additivity, but there's one axiom that's not automatic, and it's exactness. Okay, so you've tensored over something. Tensoring doesn't preserve exact sequences in general, so you might not expect that if you had exact things, they might stay exact. If R star was flat as an mu star module, then you would get a homology theory. There would be no problem. But flatness is a big condition on a ring like mu star. And the fact is that you just really don't need to ask for that much, okay? And that's the Landfaber exact functor theorem, okay? So there's a weaker condition that will guarantee that this thing here is a homology theory, and it goes as follows, okay? So you're gonna want that for every prime and every integer, then, okay, so if you take R star, this ring, and you mod out by this ideal, and so then Vn is an element in the ring R star. So I'm thinking of Vn. What do I mean by Vn? I mean, these are mu star module. It's the action of Vn on R star. You can look at the image of Vn under this map, whichever way you want to think about it. but the action of Vn on these quotients is injective. Okay. So the word is that this is like a regular sequence. That's other terminology. So if you have that, then what the theorem says is that X goes to this gadget is a homology theory. So exactness holds also. And this is a very powerful tool because you can find a lot of R, you know, a lot of R star algebra, mu star algebras, R star, that have this property but aren't flat over mu star. So now the second part of the theorem is that if E is complex oriented, and you've got, and so if it's complex oriented, you're going to get a map from mu star to E star, the map that classifies its formal group law. And if E star satisfy the conditions of 1 for that map, then actually E star homology is given by this procedure. And in that case, we'll say that E is a Line-Weber exact theory. Okay. So that's the Line-Weber exact functor theorem. And I'm going to switch slide, but this whole piece here will stay. It'll be at the top of the next slide, okay, so that we can sort of think about it while we're reviewing things. Okay. All right, so that's just the same, like I said, that's the same thing that I just annotated. Okay, so here are some examples for this. Here are some examples. So if I take, so one of the most important examples is the Brown-Peterson spectrum, BP, okay? So what am I gonna do? So I take mu, I localize it P, and I take pi star. That's just like localizing its homotopy groups, okay? So it's just, instead of being, so pi star MUP is ZP adjoin the xi's. Okay? Now, there's a clear map from that to that. And now I'm going to take this ring here and I'm going to kill all of the generators that aren't of, like, whose index here is not P to the K minus 1. Okay. Remember, I've fixed, so fix P, I guess. Sorry. Okay. So you fix a prime and then you do that. And then it turns out this ring is going to be isomorphic to ZP adjoin the VIs, okay, the coefficients of the P series. And in fact, this spectrum BP, it's called the Brown-Peterson spectrum. So if you localize mu at P, that spectrum will split. So MUP actually looks like a big wedge of suspensions of BPs. Okay, so in some sense, MUP, like the localization at P, the Brown-Peterson spectrum contains all of the information of P local MU. Okay. So that's the first example. And now once we have BP, we can sort of play and construct some of its friends. So for example, the Johnson-Wilson spectrum, EN. So if you read about chromatic homotopy theory, this thing will come up. So it's going to be the spectrum coming from, okay, so first we're going to do the map from mu star to BP. And then we're going to take BP, we're going to mod out by all of the VIs bigger than N. So that's VN plus 2, ... Okay. And then finally, we're going to invert VN. So if you mod out by all of the VN plus 1 and you don't invert VN, you're not going to get Line-Weber exactness. So a good exercise is to check these conditions for these two theories, to check this. Okay. Now, and its homotopy group are isomorphic to this ring. Okay. And now, like, what have you done? You forced the coefficients of xp to the n, you forced it to be a unit, right? So E theory has height less than or equal to n. Okay. So that's the Johnson-Wilson spectrum. All right, so these theories come up, they'll come up next time. But for now, the goal is to introduce a bunch of new spectra that you wouldn't have thought of if you didn't maybe have this machinery. Okay. But okay, so on the next slide, I'm going to introduce Morava-K theory. But I'm going to go, yeah.
Yeah, I have a question, and again, maybe I'm jumping the gun. To what extent are Line-Weber exact theories classifiable?
Okay, I can think of, so like you want to like classify all mu star modules that are, I'm going to tell you, okay, so I mean, one thing is like they're like the flat maps. So if spec R to MU, like I think the theory is line exact if they're like the flat maps from spec R to the moduli stack of formal groups. But that's like an answer that I would hate if you gave to me. So, I mean, there's like algebraic geometric perspective to it, right? But that doesn't really like, so, but if you wanted to know like, okay, which rings, like, can I just say which rings are line variable exact? I don't know the answer to that question. But look, if you can identify the VNs, then the condition is easy to check, right?
Right. Okay.
The hard thing is identifying the VNs. But the thing is, you don't need to do, I did with MU because I didn't talk too much about BP, right? I've sort of spent a long time introducing MU, so I used MU because I think it's more familiar at this point. But you can do all this with BP also, okay? So you can just say like, instead of like, you can look at BP star modules and do that. And then like, if you have a BP star module, it's like, if you have a good description of your module, it's a lot easier to tell, to test this condition because the VNs are staring at your, they're staring at you, okay? Because they're the generators. So that's that, okay? But I'm sorry, that was sort of a roundabout non-answer to your question. So.
Okay, thanks. And looks like, David, do you have a question?
Yeah. Can you guys hear me okay?
Yeah.
Okay, so I have two questions. One is, I mean, my first question is the VNs, are they generalizing something more classic? Because I feel like VN is already a notation that was used sort of before this part of the theory was developed, and I'm wondering if there's something like just with respect to regular old homology that those guys are generalizing. I have a second question.
I don't know for sure, but I'm not sure that it's true that the VNs are more classic. That's the part that I don't know that it's, so I don't know. So why do you think the VNs are more classic? Like this MU story is it's pretty early on in this business. So
yeah, I guess, right. Okay, maybe it's just that your presentation of the VNs,
yeah, my presentation of the VNs is maybe not so classic.
Right, okay. But it's the same VNs that we learned about in the classic approach.
So the VNs are, so VI is, sorry, that's not a good. So VI is unique mod PV1 up to VI minus 1. Okay.
Okay.
So I haven't, the choice I made, I mean, it's not clear to me that it's, I don't think it's either the Hazel-Wilton or the Iraqi generators.
Right. Okay.
But mod this ideally would be. Okay.
Yeah, thank you. Thanks for reformulating my question into the actual question I was asking. Yes, that was exactly it.
Yeah, no, it's not easy. I don't know. Like I don't think so, but I don't know. Yeah.
Okay. And then my second question is, the Johnson-Wilson and Morava-K theory spectra have always come at me as very unmotivated, because it's like, here's this thing that you wouldn't have thought of. Oh, and then later on, there's all these applications for it, and it's used in all these computations. So I guess my question is, how would you come up with these things the first time around?
Oh, I don't know. You're gonna have to ask Johnson-Wilson. Like, look. So maybe something that you would come up is like Vn minus 1 BP. Like where you sort of isolate the height n part.
Yeah.
Height less than the n part. This has the same Gauss-Field class, but it's much bigger. So it's kind of like this. You've just like, you kind of stripped away all the things you didn't need.
Okay.
But I don't know. You're gonna have to ask Johnson-Wilson.
All right. Thanks.
Okay. Or like, I don't know, maybe in the Ravenel's paper somewhere, it's in there too. Like, so one of the landmark papers is called Localizations with respect to certain periodic blah, 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 blah. So that's Ravenel. It's on my website. So that's the classic paper, and it's a really beautiful paper. So you might find some more answers in there. Okay, so I'm going to move on. So now I'm going to talk about the Morava-K theories. They're not Landweber exact theories, okay? So I went to the bottom of my slides. So they're not something that you won't, the procedure that I described, you won't won't satisfy the condition that I was putting on the theories. Okay, but okay. So to construct them, so I'm going to be vague about the construction. There's various ways to do this. So if you look at the classic literature, you'll see like the Bass-Sullivan construction. But I'm gonna, so I think that at this point, if you want more detail, I'm gonna send you to lecture 22 of Lurie's note on chromatic homotopy theory, okay? Like in the modern world, we have good symmetric models of spectra. So we have good categories of spectra where you can talk about module spectra and like everything you can do rigidly. And in these categories, you can take things like mod out by elements and invert things like very, very well, okay? And so the sort of more modern way to construct the Morava-K theories is to do it in one of these categories, okay? So what do? So you fix P and some N, and the nth Morava-K theory, you're gonna construct it from the P localization of MU, and you're gonna kill everything except xp to the n, okay? So Vn might have not been xp to the n on the nose, but once you kill everything else, it will become that, okay? And then once you're done doing the killing, or look, maybe I got the order wrong. Maybe you kill all of these, you invert this, and then you kill all of these, okay? But you do some process, and then you invert this Vn, okay? And all you're left with, well, you've modded out by P, so you get Fp, and all you're left with is a theory which we call Kn, whose homotopy groups is this ring here, okay? So in this lecture, Lurie describes the process with more details, okay? And you get that it's a homotopy associative ring spectrum. If P is odd, it's homotopy commutative. If P is 2, I don't think it is. But there's more details in the lecture notes. And it's complex oriented, and its formal group law looks like this, okay? So it starts with Vn times x to the P to the n. So this formal group law, if we think about, well, Vn is a unit by construction, right? We inverted it, okay? And all of the VIs before, like the coefficients of the xp to the n before are all 0, okay? So it has height exactly n. Okay. So this is like your prototypical example of a theory that has height exactly n. So for example, K0 is rational cohomology. K1 is really closely related to KZP. So pi star KZP can't quite be what I just described, right? Because that's FP beta plus or minus 1, where beta is in pi 2, okay? And pi star of K1 is FP V1 plus or minus 1, where V1 is in pi 2 times P minus 1. Okay, but you can think of V1 as beta to the P minus 1, okay? So this guy, K1, is a summand in mod PK theory, and it's called the atom summand, okay? K infinity HH is H Z mod P, okay? And K2 is K2, you know, you probably don't know about K2 before today, or, I mean, you did, but like, there's no better description. There's not some cool theory out there that we had that was called K2, and then suddenly we found a new name for it. And the same for K3 and so on. Okay, so these are new theories. So these are the Morava-K theories, and they satisfy a lot of nice properties, which come basically from, like, look at the coefficients here. The coefficients are graded field. Okay, so that's nice. We know that working over fields makes life easier, and it's true in homotopy theory also, okay? All right, so let me talk about some properties. So let's see. So first, let's make two definitions. So so this is like a lot of words, but roughly a spectrum is gonna be finite if it's isomorphic to the suspension spectrum of a finite CW complex, okay? And it's gonna be P-local finite if it's the P-localization of the suspension, isomorphic to the P-localization of the suspension of a finite CW complex, okay? Roughly, you can go look at more detailed definitions out there, okay? I don't know, you can look on NLab. There's a nice discussion about that. If E is a field, So that's the definition of what a finite spectrum is. Now, what is a field? A field is going to be a theory such that E star of X, so the homology of X is free over E star for any spectrum X. Okay. So if you think about so fields in our usual sort of life, modules over fields are all free, right? So this is the equivalent statement, but sort of formulated in spectrum. Okay, so why strange module? Yeah.
So you said that to be a field that has to be true for every spectrum X. Is that right? And is it sufficient to test that on just suspension spectra, or just on or do you actually have to check it for every spectrum?
I don't know.
Okay, but it is for every spectrum, not for every space.
I said for any X, yeah, for any X, not finite X, yeah.
Okay.
Yeah, I think you probably have to check for more than that. For the I don't know. So, all right, so can is a field. Okay, so that's one of its properties, and in fact, it's the prime field. They're like so they're the basic fields. Any field E is a wedge of suspension of the cans. Okay, so if you thought fields were confusing, well, be deconfused, because they're just suspensions of wedges of the cans. Okay, so you can imagine all the fields in your head right now, if you can imagine can. Okay. So can star has a Kunith isomorphism. So if you take the smash product of two spectrum, then can star of that is just the tensor product of the theories. Okay? And anything that has a Kunith isomorphism is a wedge of suspensions of the cans. Okay, so these are the theories that have Kunith isomorphisms.
And yes.
Yeah.
Earlier, you had this example where it was like if E has a complex orientation, then E star of a product of CP infinities was what I would expect from Kunith.
Not just CP infinity.
All X and Y. I see. Okay. Thanks.
Yeah. So now they're orthogonal in the sense that if I take can and I smash it with can, that's trivial if n is not equal to m, and p is not equal to q. Like if you're looking, I'm talking about one prime, but it's also true if you smash across different primes. Okay. And finally, so these theorems here, they're in that Ravenel paper that I mentioned, and this one is also. So if X is finite, now you need finite for this to hold. Then if Kn star of X vanishes, so if X is Kn star acyclic, then it is Kn minus 1 star acyclic. Okay, so they're orthogonal, but they talk to each other in a strange way. Okay, I don't have a really good feeling for. So I wish I had like a really good intuitive explanation for or another example of a place where you have these primes that talk to each other but are orthogonal. I don't. I'm sure they're out there, but to me this has always been a bit weird. Okay, and these things are not super easy to prove. So now I'm going to skip this because of time. Okay. I'm going to come back to that next lecture. So I'm going to come back to that. Okay. But these are some of the properties of the can, and I want to, I'm going to run out of time. Let's see. Let me do this slide. Okay.
Yeah,
okay, so now
I do think it's best to end more or less on time. I mean, if you need a few minutes to wrap up, that's fine. But let's not.
Yeah. So I think I'm just going to do the slide and stop.
Okay.
Okay. So suppose that you have two formal group laws, and so we're going to say, we talked about morphisms. We're going to say that an isomorphism is strict if it just starts with X. Okay. So these were power series. Okay. So I can form a new category. It's going to be a subcategory of the formal group laws on R. It's going to have all the same objects, but the morphisms are just going to be the strict isomorphisms. Okay. So now if I have a ring that gives me a groupoid, okay, because this thing has only isomorphisms, so I get a functor from graded rings to groupoid. And And then Quillen's theorem, the sort of last punchline of Quillen's theorem is that if I look at mu star and mu, well, that's isomorphic to a polynomial ring like so, okay? Where the BI, you want to think of them as the coefficient of the universal strict isomorphism, okay? So if you had a strict isomorphism, it's a power series, and these BIs are like the sort of stand-in coefficients for it. And what does that mean? It means that if you have any ring homomorphism from mu star and mu to a ring, then what does that carry? That carries the data of two formal group laws and a strict isomorphism between them. The strict isomorphism is sort of encoded by the BIs. And if you know the BIs, you know what the endpoint has to be. Okay? So this functor from rings to groupoids is representable. Its objects, well, we already saw that's mapped from mu star to r star, but the morphism of the groupoid are the morphism from mu star and mu to r star, okay? And this groupoid, it represents a stack, and what the stack is MFGL. I will draw some pictures for the stack. You don't have to sort of be comfortable with stack to be with me for the rest of the semester, the 2 courses, okay? So, but it sort of encodes all of that. The objects are these formal group laws, and the stackiness is these strict isomorphism. Okay, so I'm gonna stop here and say thank you. So that's Jack Morava.
Okay, I'm going to unmute everyone so we can thank her again. Okay, and I will mute everyone again to cut down on the background noise. Okay, all right. Do we have other questions for Agnes? Right. I would like to make a comment today that there were a lot of questions during the presentation today, which I think is great. I know that presenters appreciate that. They get some sense of feedback that there really is an audience out there, because it's kind of strange talking to a computer. So thanks to everyone who contributed questions. They were all great, and they really contribute to all of this. Okay, so I guess we'll wrap it up here, and we will meet again on 5 days, next Tuesday, for part 3. Okay, thanks again, everyone.
Thanks for coming.
Okay.